the size is very small, the class size is very, very small. Rather than typing it, better unmute yourself, ask a question, and build some foundations in this particular domain of data science and machine learning. I hope you will follow that. Does that make sense? Sai Dhanush, can you hear me? Would people respond, please? Otherwise, how this lecture will continue? Okay, you can't unmute right now. Somehow give a response, right? Okay, I'll start the session. So yesterday was the first session. We just commences the course, right? And we looked into what will be covered in the course as such, what are the books that we are going to follow, and we started off the basic understanding of what is the machine learning, why machine learning, right? What is its connection with uh, other technical areas such as linear algebra or statistics or programming and so on, right? We looked at different, I'm just going through quickly, right, what we have covered in the last session. I'll not go into the details, and then once we start the new content, then I'll go into the details of that. So this snapshot basically talks about that where I can use machine learning, right? There's one very, very important application which all of us might have experienced, right? Or if you have an email, Gmail, right, or any other kind of an email, right, you must have experienced that there's a certain emails going to your inbox while certain emails are going to your spam also. How does this email application finds that this email should go to inbox while this email should go to your spam, right? So this kind of a problem can be solved using machine learning, right? Maybe largely, if you must have seen, right, promotional emails largely go towards spam. So they might have keywords like credit cards and maybe your personal pre-approved loan and something like that, right? Uh, those kind of keywords will be there, and basis that it decides, okay, this should go there, right? But we can formalize this using machine learning. How to do that? That we have discussed in the last session also. Uh, Before that, we need to just brush up the definitions of machine learning, and then we'll come back. This term was coined in 1959 by Arthur Samel, as I told, right? He said that it's a field of study that gives the computer the ability to learn without being explicitly programmed. Normally, what happens is, if I want to get some computations done from a system, I will write a program, I will feed the input, I'll get the output, right? And that program instructs the machine or the computer how to perform, right? What sort of computations to be done. But what machine learning says, we are not explicitly giving a set of instructions to a machine or a computer. It has the ability to learn itself, right, without being explicitly programmed. We will give it a kind of a program using which it can learn itself, right? But I'm not going to tell, okay, we want to solve this kind of a problem, you follow these rules. No. So you see, it's a quite an old term, but it became popular only somewhere in the last decade, right? From 2014-15 onwards, I'm seeing this is largely adopted in the Indian industry. And why this transition took a lot of time when the concept was conceived of already in 1959. The reason was simple reason. If you have if you have seen machine learning problems, right, they work on lots of data. Without a data, it's not a good idea to come up with a machine learning solution, because the performance that we are expecting may not be very good as such, right, or may not meet our expectations as such. Secondly, when there is a lot of data, you need to do a lot of computations. During 1960s, we neither have that much data nor we have the hardware. When I say hardware, it's all about storage as well as computation. But now, over a period of time, almost, if you see, the storage cost has come down, the computation cost has come down, right? We have more advanced processors, we have different ways to store the data, right? So storage per GB cost has come significantly down. So all these things have led to this transition of this concept to a practical implementation as such, right? These are some of the examples on which machine learning can be applied. One was, of course, email classification, whether you want to categorize a particular image as a spam or not. You want to translate a text in English to Hindi, right? You want to generate text transcripts from an audio, which is right now happening in this particular session as well. You want to find out from the medical images that a particular patient has a tumor or not, right? Then, of course, in self-driving cars also, we want to know from the images and the radar info what is the position of the car as such, right? All these can be solved, all these problems can be solved using machine learning, right? As I said, machine learning needs lots of data, right? So let us understand one more definition, right, which we covered in the last session, which is given by Tom Mitchell, who is considered to be as a father of machine learning. He defined machine learning tasks, which is given by three different variables as such. These variables are P, T, and E. P stands for performance, T stands for task, right? And E stands for experience. A performance of a machine learning algorithm at a certain task is expected to improve with experience E. That's what it is, right? When I'm looking at a machine learning task such as email spam filtering, what I need certain set of email data, historical data, which already has certain labels, output labels. Okay, these are the characteristics of an email, and this was labeled as a spam, and this was labeled as a genuine email, right? So maybe that is done by humans. And once I have a certain amount of data, right, which can categorize my emails as spam, I mean, which has a good balance of spam and genuine emails, right? I can feed that data to a model. I'm not feeding a program. Now, from that data characteristics, it wants to learn certain rules. Okay, if these are the characteristics, I have to classify it as a spam. If these are the characteristics, I have to classify it as a genuine email, right? So in this case, now what is performance? How accurately my model is able to classify an email as a spam or not spam, that is the performance, right? Task is the classification task, whether it's a spam or not spam. How accurately it is able to do, that is a performance. What is the experience? The amount of historical data that I have, that is experience, right? And similarly, we talked about certain examples like playing checkers, recognizing handwritten words, driving on a 4-lane highways using vision sensors, right? All these uh, examples, right, or the applications or the problems, right, which we are looking forward towards a better solution, can be solved using machine learning, right? Any questions? Any questions from anyone? Okay, all right. I'm again repeating, if there are any questions, Preferably unmute yourself and speak. I'm just repeating the little bit of last session so that we feel connected. Then the traditional approach to spam filtering could be like, I can write certain rules. I can write a if else kind of a program. If a keyword is appearing in this particular email, right? Or I can hear some sound. If there are any questions, please do let me know. Otherwise, please keep yourself on mute. Okay. So what I was saying is, basis certain keywords in the email, right? I can write certain rules. Okay, if these are the keywords that exist within the email, probably it is a spam email, and basis that rules, I'm going to evaluate whether it's a spam or not spam. And if I do so, I may end up in writing very complex rules myself, right, as such. And it becomes very hard to maintain such rules. Now, those may be working correctly, but let's say there is a change in those spam emails. There's a change in the pattern on those spam emails. They started using some other keywords and so on. What will happen? Again, you will have to update the rules and so on. So, in order to avoid such updating explicitly, right? I can go ahead and apply machine learning. Needless to say, I need to retrain the model whenever there is a new data coming in. Of course, the model will learn the rules by itself, right? But in the traditional way of writing rules, what is happening is I'm going to supply the rules. And then we also evaluate the model. When I say evaluate, it means I want to check how accurately it is able to classify in case of an email spam filtering problem. How accurately it is able to classify if it is within the reasonable accuracy, right? I'll say, okay, I'm going to deploy this model. This is ready. I can launch it. If it is not within the permissible limits or the expected limits of the accuracy, I'll say, okay, no, I need to write the rules again. I mean, I need to revisit the characteristics of the email and write the rules again. This evaluation part also we follow in the machine learning problems, right? When we use machine learning, we are going to follow this evaluation rule also. And there are metrics, right, which we can use to evaluate the performance of a machine learning model. You look at this now, instead of writing rules, I'm training a machine learning algorithm, right? I'm building a model. When I'm building a model, right, it will automatically learn certain rules. The rules which I was explicitly supplying when I was not using machine learning, now the machine will learn itself those rules, and I can always evaluate how good my model is in terms of classifying those emails. And if I am able to achieve the reasonable accuracy, I can go ahead and launch the model. Otherwise, I need to improve it, right? Now, whenever there is new data coming in, right, I can feed that updated data to this ML algorithm as such. It will be automatically learning the new rules, right, as such. Again, I can evaluate the solution and launch it. And if there are frequent updates happening, I can kind of put it in the form of an iteration that which you can see in the second diagram, and it will automatically be able to accommodate the new rules which are coming in the new data as such, right? That's what the machine learning approach is. Another good example is we want to recognize handwritten digits, right? Because people have different handwritings and we want to recognize these digits. What we need is again the historical data to make it a machine learning problem. I want the samples of the digits. Maybe I can ask 100 people to write the digits, right? I might collect 100 samples of each digit and feed it to a machine learning model. Machine learning model will learn the characteristics out of it for each digit, and then it can be used to classify on unseen data. So these are some of the other use case scenarios, right, of machine learning. You can go through it. We have already looked into it in the last session also. This is again, how do we actually, what's the kind of a cycle that we have while we deploy those machine learning models as such, right? So first of all, you study the problem. Once you have studied the problems, you have a lot of data using which you can train a model. And once the model is ready, the solution is ready, right? You want to inspect the solution. Inspecting means evaluate, right? If needed, you will understand the problem better, and uh, then you are not, if you're not able to achieve the reasonable performance with your model, this will go into the iterations as such, right? So these are the ML use case scenarios, right, where you will say, okay, there are a lot of use cases where we can use ML. Now, can somebody tell me what are these use cases from the images? Don't keep quiet. I'm looking forward to an answer. Hello? Can't you speak, please? Otherwise, it's a monologue, right? I don't like it much.
Yes,
Robotics?
sir.
Yeah, please go ahead.
So, sir, the second image, it is like a speech recognition.
Correct?
Uh, Third, bioinformatics or
Correct.
human medical something.
Correct. Maybe we want to
And
know the genetic sequence, genomic sequence, and all, right?
yeah,
Gene engineering, correct. Also, Sai Dhanush, fine.
the fourth one is somewhat related to discovering patterns.
Correct.
And the first one, I'm not sure, maybe some autonomous systems.
Okay, fine. Good, good overall. What is the meaning of it is a good interpretation, right? So it simply indicates the use case scenarios where machine learning can be applied, right? It could be speech recognition, it could be recognizing genomic sequence, comparing genomic sequences, and all the pattern recognition. And what kind of image it is? First one. The first one, what kind of image it is? Do you think it is related to something related to space?
Yeah, so
Yeah, right.
some
So they
object detection.
correct. Okay, rover. Okay, fine, good. So yes, it is something related to space, right? Maybe it is capturing certain images, right? Capturing in a sense, there is some other device which is capturing, but it is receiving those signals and all, and then maybe whatever data it has collected, we can sort of uh, do some analytics on top of that, because those images will be huge, right? And for that, we need kind of good amount of computation power as such. So when to use machine learning, problems for which the existing solutions require a lot of hand tuning and long list of rules, right? That is one way. Complex problems for which there is no good solution at all using traditional approach. Traditional approach means writing deterministic algorithm. Now I'm not, let's say you want to write a program to find factorial of a number. I know I have a very good deterministic program for that we have learned in C language, right? I cannot use, I should avoid using machine learning for finding out a factorial of a number. I should not have that historical data. Okay, I have historical data of, let's say, 100,000 numbers for which I have the factorials, and now I will apply machine learning on it, right? There's no need of doing that because I already have a deterministic solution, right? So I am able to solve it with a traditional approach. I already gave you example last time. When you want to go from one place to the other place, let's say from your home to office every day, it may take different amount of time, right? So for that, I need historical data. There are some external variables, right? If there is any event going on the city, if there is any accident on the road, if there is, it is a cloudy day or there's a rain there, right? The weather is not very conducive as such, right? So if there is any politician visiting that particular area, right, lot of variables will come in, and you cannot simply write a kind of a deterministic solution for that. So what you need is historical data, some impact of external variables, right, using which you can model a machine learning problem and then predict how much time it will take. Changing environments, right? As I mentioned, a politician visit, right? Environment got changed. For a deterministic solution, you will have a fixed set of inputs, right? Get insights about complex problems and large amounts of data. Certain problems which cannot be solved with a traditional approach, and where the amount of data is huge as such. What should we do in that case, right? Gradually, we will learn, right, how we are going to solve, but with small data sets initially, right? And then you can practice it with some real life data also. Just give me a moment, right? Just a minute. Somebody's here now. Okay, let's continue. So where does ML fit in, right? So a lot of things we require for machine learning to work as such, right? There's applied math, there is statistics, there's a computer science, right? Neural networks, right? Psychology, physiology. Uh, there are certain applications where there are new challenges coming in as such, right? So all these things, I mean, there are certain areas from which you have to apply those concepts in order to solve a machine learning problem, like applied maths, linear algebra, optimization things, statistics, sampling, estimation techniques, right? All those things, computer science, writing an algorithm, program, and so on. And in addition to that, now where you will apply certain application where there are new challenges, right? There is another class of things, right, which is called as a neural networks, which solves kind of a problem similar to a human brain kind of a thing, right? We will look into it also later on. There is some portion of this neural networks also, ANN, artificial neural networks, we'll talk about. These are the application domains, which I'll not go into the details of it. These are the areas in which machine learning can be applied. How to apply it? You better know, right? You have already given me an example at side and you said robotics. How we can apply it in e-commerce? Maybe I want to predict, let's say, the forecast, sales forecast, specifically during big billion day sales, right? I want to know how much sales will happen, how many orders are expected to arrive. Basis that maybe I need to align my executives to deliver them on time also, right? So I can better plan the things. In finance, maybe I wanted to check a particular profile whether it is good to give a loan to this particular candidate or not. Basically, I want to predict whether this candidate will default or not. Space exploration, right? We have already seen that slide. Space exploration. Then any kind of creative arts, we can also apply this, right? So lots of areas as such. A very good example that we can talk about under machine learning is a classification problem, right? We've already learned one example of it, and that was in the form of email spam filtering to classify the emails as spam or not spam, right? So in simpler terms, classifying is basically classification is kind of a task of assigning an object or an event to one of the fixed set of categories. In case of the email as spam or not spam, there are two categories, right? So we have predefined labels with us that either it is this class or this class. When I am recognizing handwritten digits, right, I have predefined labels from 0 to 9. There are 10 classes total. So a digit can be recognized as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have predefined labels with me. These are the categories as such, right? So I can use this classification across many domains again. First is medical diagnosis. So given a particular patient data or the symptoms or the test results, the model can classify whether a person has a disease or not, right? That's one thing in credit card applications. The system can classify whether the transaction is valid or it is a suspicious transaction. Fraud detection in e-commerce. The model can decide whether the transaction is fraudulent or genuine, right? Many times what happens is, if you see, sometimes people will order, right? And once ordered, right, nobody is there to receive that. There is an address given, everything is given, but there is nobody to receive that. Somebody goes, there's nobody to receive. Or, no, I have not ordered it, something like that. And when this happens 4, 5, 6, 7 times, these e-commerce organizations, they have sufficient data and now they will blacklist that particular address, right? So there are algorithms which can automate these things basically. In cybersecurity, how you can apply this? You can use classification for worm detection in maybe network packets. I hope you know, I mean, any sort of threats within those networks, right? It can detect. So it can classify whether this data which is incoming is safe or malicious. Recommending articles in newspaper, recommending books and all these fields makes use of machine learning, right? So this is all about this classification. There's another set of problems where we can apply machine learning is which involves planning control, right? Planning control as such. Now, the goal here is slightly different from what the classification problems have. So here, instead of assigning the labels that, okay, this is a spam or not spam, the system is actually expected to take a sequence of actions in a particular environment in order to achieve a specific goal. So basically, it's like a decision making over time. So let's say you play a game like chess. You're not just making one decision. You are actually planning multiple moves ahead. These are the moves I'll do, right, to win a particular game, right? So how an AI learns? An AI system learns to plan the actions step by step. This. Now, you must have seen balancing a pole. This is a classic control problem as such. The system continuously adjusts its sections to keep the pole stable. Right? Driving a car, the system needs to make real-time decisions when to accelerate, when to brake, when to turn based on the environment. Right? So these are certain set of problems which comes under planning, control, and problem solving, where the system needs to take the actions rather than simply labeling them. Right? This is another set of problems that can be solved, right, using AI and machine learning. Okay. Next is, as this slide title indicates, automatic speech recognition. So what the slide shows, any idea?
How speech is recognized through machine learning.
Yes, correct. How speech is recognized, very nice. That's it in simple terms. There are terms written now which may be new to you, right? The goal here is simply, right, as you mentioned, convert a human speech to a text, right? Let's say I'm speaking, and if you see the transcript, it is generating the text. So that's a perfect example, right? So what do you need is first the speech signal, which is basically an audio waveform. This is an audio waveform signal as such. The signal is then passed through a feature extraction stage. Now, what do we mean by feature extraction? What are the features that exist in that audio wave, right? It will extract that. So the raw sound is actually getting converted into a spectrogram, which is a visual representation of a sound showing how frequencies change over time. Then that is fed to the neural network. A neural network is a kind of a, you can say, a kind of a algorithm for training a model, right? Neural network will actually learns to map the patterns in the sound, right? And it will be able to map it to certain states. And these are the some basic units of, you can say, speech, right? Um, you have a audio signal, fed it to feature extraction. Feature extraction is going to extract certain features, basically converting a raw sound to a spectrogram, which is the visual representation of sound showing the how frequencies change over time. Neural network will learn certain patterns out of it, and it will now be able to say, okay, this is the frequency, this is the kind of a word that can be associated with it, and so on. So after this, a decoder is there, which processes these predictions and tries to form a meaningful sequences out of it. And finally, the transducer and the language model, which help to convert these sequences into proper words and sentences, right? Maybe it will also take care of the grammar and the context as well, right? So what it is saying, this is a audio wave of this particular word, hi, how are you? And this is fed to this kind of an, you can assume as a abstraction thing, right? And this is the output that you are getting as such. Right? Now you see this term mentioned, deep learning. What do we mean by this? Have you heard this term, deep learning? Hello? Am I audible? Just let me know if you've heard this term deep learning. Accordingly, I'll go. Hello? May I have some response, please. Hello? Should I continue then? Can somebody please respond if you know this term deep learning or not? Yes, okay, you know. What is deep learning? What is your understanding of deep learning? That's it. Please try to communicate, right? Just saying few words and then staying quiet, keeping quiet is not an option. Either write in the chat box or speaker. Vasu, yes, what is deep learning? It's a subset of machine learning. Okay. For what purpose it is used? So when you want to do extensive computations as such, right? And you want to do it in certain form of a layers, right? There's an input layer, then there's an input layer, then you have some intermediate layers, right? We use neuron-like computation to store past data, patterns, and data is processed. Exactly. Exactly. So you have some input layer, right, where you will feed some data. Then in between there are hidden layers, and finally there is an output layer. So it's not simply input and output going. You don't have simply one input and one output as such. I mean, when I say one input, one output means the way we have seen the typical machine learning, right? There is one set of input data. I am giving it to a model. Model is giving me an output. Here I have multiple layers in between. I am not simply feeding it and getting the output. That's the ultimate goal, right? Output will be there, but it is through hidden layers also as such. The word hidden layers is being used. So it's a kind of a layer. I have some input here, then maybe another layer here, then another layer here, and finally I have the output as such, right? So these layers are also connected. Kind of this, right? We will do it in detail, right? What does it exactly means and how do we first we will understand some basics, then we will move towards that, right? Okay, now within this hidden layer, right? There were actually what was there before deep learning, there was something known as a baseline models, Gaussian mixture model, right? These were used and it has a baseline error rate of 15.4%. With deep learning, right, as I said, there are certain hidden layers apart from input and output, right? So if you have one hidden layer, this was the error rate. Once you started increasing it, it is reducing, right? Till this point, it has reduced. So the performance is improving significantly as I'm increasing the number of layers in between. So that's why the chart says breakthrough in automatic speech recognition. Still, there are errors, right? Of course, you will see certain words not written properly in the text when I speak, right? But still, it is doing it for most of the words, right? And we have said that, okay, this is reasonable accuracy to go ahead with speech recognition, and let's do that. That's what it is. So with one layer, it is 16%. As with you add more layer, the error reduces. The best performance is around when you have 8 layers as such, right? So this is from the reference from a particular paper. So now you see, we are feeding a raw data, audio waveform. Model learns out of it, right? That's the beauty of machine learning. Now you see the real life impact of this in the speech technology, right? We have it in our phones also. Right? We have, if you look at, like all these are the different products, or you can say the platforms where speech technology is being utilized, right? The smartphones, you can see user can speak commands instead of typing. You must have seen Google now, the Siri, right, which act as an intelligent voice assistant overall, right? If you look at this Windows, there was another one, important one, Cortana, if you remember. You can ask questions, set reminders, send messages, anything you can do using these voice assistants, right? There are tools like Dragger dictation, right, which allows the users to convert the speech into text. Again, the speech to text, very useful for writing emails, documents, and notes without typing. So these are all the tools actually which have make use of the speech technology, and kind of they're being used in real life, right? So what deep learning has done, deep learning has made this speech recognition more accurate, more reliable, and usable in real world systems. And this is what this chart indicates. Now looking at another application.
Excuse me, sir.
Yeah.
So can you go back to the last slide where we were extracting speech recognition?
Yeah.
Yeah. So, sir, where do we have this hidden layers in which stages?
A neural network.
Okay.
This network, when we will expand it, right,
Mm-hmm.
the hidden layers will be here, where the learning happens.
All right.
Yeah. So neural network, if you have one hidden layer, this is what it is, right? So if there are two, this, four, this, eight, this, and so on. This is what it means. So number of hidden layers we can specify. That, and then it will take more time also when I'm increasing hidden layer, because more learning is happening, right? More computations are happening. But as I'm able to improve the performance parameters, and even if I'm able to do the computations with that reasonable amount of time, I'm good to go ahead with that, right? That's what they are doing. Understood?
Yes, sir.
All right. So another thing, right? What is this? Visual question answering. So given these set of images, what a machine learning can answer, machine learning models can answer. So we are not just recognizing the object. What we are trying to understand is the scene and the reason about it. If you look at the first image, we see a person holding bananas like a statue. System can answer questions like what is mentioned, what color are her eyes, what is the statues made of. So what it needs a visual recognition and contextual understanding as such. Second image, right? We have a pizza. The question is, which we can answer is how many slices are there? Is this a vegetarian pizza or not? So model must count the objects and understand the content also. How many slices are there? Looking at the toppings, it should be able to identify whether it's a veg or non-veg. If you look at the third image, person is sitting under a tree. Now, looking at the scene, right? Is this person expecting a company? These are the questions, right? What is under the tree? Now, this becomes more complex. It requires reasoning as well as inference. It's not just about looking at the image, right? Because we're trying to infer, is the person expecting a company? Last image now. We see a person outside, right? One of the questions that it includes is, does it appear to be raining, or does this person have 20/20 vision, right? So the system must combine the visual clues with the real world knowledge. So what is this visual question answering is basically happening here is, when we try to do this, is it combines kind of a computer vision and natural language processing. So the model must understand the image, understand the question, and then generate the correct answer. So this is also with the help of deep learning, we can do this. So deep learning is not just about seeing or hearing, right? Hearing, I'm talking because we have looked into speech recognition earlier. So it's all about understanding and reasoning across multiple types of data. It's not only speech recognition, right? In deep learning. Deep learning can be used in variety of applications. Then autonomous car technology. This is again one of the most powerful applications of deep learning, you can say. Multiple capabilities here we want: vision, planning, and control. All three come together. The kind of problems it can solve, right? We saw under vision, planning, and control. So if you look at the top left image, this shows the laser terrain mapping as such. The car uses sensors, right, to scan the environment and create a map of roads, obstacles, and surroundings. That's what it is doing. Next, on the right side, we see a path planning also. So once the car understands the environment, what it needs to do is decide where to go, which path to take, how to avoid obstacles, and so on. So we have to compute the optimal path in real time. Then comes as learning from human drivers. The system observes humans drive, right, as such. At what speed? How do they apply brakes? How do I have to make turns? Learns patterns. And this helps actually the models to behave more naturally and safe. So this is a sort of experience as such, right? Then finally, the bottom right shows an adaptive vision where the deep learning helps the car to identify the roads, detect obstacles, understand, you can say, terrains, right? And even in challenging environments like rough roads or poor lighting, right? The system should be able to proceed. That's what we are trying to look at. Now, these are other contemporary ML based solutions, right? Optical character recognition, product image classification on a product line, uh, then detecting tumors in brain scans, information extraction from document images. Basically, all these applications can be built using machine learning. Some of these are repeated. We have looked into them earlier also, but these are the applications for which we can use machine learning. Now let us look at types of machine learning systems, right? Now, first thing is, it's a kind of a broad field, and we can say there are many different types of ML systems as such. The first way is to based on the training, whether or not they are trained with human supervision, right? Basis that we have categories like supervised learning, unsupervised learning, semi-supervised, and reinforcement learning. Second way is based on how the data is received, whether or not they can learn incrementally on the fly, right? Whether there's a continuous stream of data coming in, like what happens is typically there are sensors keep on capturing the data and sending it. That's a continuous stream of data coming in, right? Or is it just a batch learning? Sorry, how they generalize, that's another important point, right? Third is how they generalize, how the system generalizes. The system makes predictions, right? Now, whether they work by simply comparing the new data points to the known data points, or instead they detect patterns in the training data and build predictive models, much like the scientists do, right? So it's sort of instance-based learning where the model compares the new data with the stored examples, or it's a model-based learning. It builds a general model by identifying the patterns in the training data, right? So machine learning systems are not all the same. They differ based on how they learn, how they process the data, and how they make predictions, how they generalize, right? So we are going to look into each one of these in detail. What is supervised, what is unsupervised, semi-supervised, reinforcement, and then based on stream of incoming data and how they generalize, right? Before that, let us look at basic ML terminologies. Now let us look at these labels. The first one. The first term under terminology is label. Label is something that we are trying to predict. Like in case of email classification, right? Spam filtering. I am trying to predict the label whether it is a spam or a genuine, right? That's a label. It's a kind of a feature, right? But it is an output feature. This is an output of the model, right? Now, if I am going to, let's say, predict the house price, the price of the house is a label. I want to identify what kind of this digit is, handwritten digit, right? So from 0 to 9, what are those? Those are labels, right? So now I think we fairly know what a label is, right? Next comes is the feature or the attribute. Generally, features are considered as input variables. Basis which we are going to predict the label. And label is my output variable. So a simple machine learning project might use a single feature, while a more sophisticated machine learning project would use millions of features specified as x1 to xn. Like for email spam classification problem, the words in the email text could be one of the features. What is the sender's address? That's another feature. Time of the day the email was sent. That's another feature, right? These are my input features. Basis this, I am going to predict a label whether this is a spam or a not spam. For another example is, I want to predict the price of a used car. What is the input data I want? What is the mileage of the car, right? How many kilometers it has run? That's another important thing, right? Uh, how old it is, the age of the car, which brand it is, right? Has it met with an accident in the past? This is also a relevant feature, right? Was it used for as a transport vehicle sometimes or not, right? So all these are the input features that we need in order to predict the price of a used car. So there are certain input features, there is certain output feature, right? So input features are normally represented as this, right? We can represent it with bigger X set of features, right? Y is my output features, which is a function of X, which is basically a function of x1, x2, x3 up to xn. This is how we represent it mathematically. I hope it is making sense.
Sir, I have a question.
Yeah, please go ahead.
So we learned about performance, task, and experience. So
Yeah,
feature or attributes can be termed as experience, is it?
yes, these are a part of data. Yes, these are experience. Experience is not only attributes. Let me tell. Yeah, we get a data set, right?
Okay.
We generally have a data set. Data set have these attributes. Now, let's say I have a data set of the old cars which were sold in last 5 years. I have their, let's say, car registration number, right? I have what is the mileage of the car, what is the age of the car, uh, then brand, has it met with an accident or not, right? There could be more features, right? I'm just writing. So what will be experiences like there will be one record like, okay, let me put serial number here. First record is this, second is this, third is this, fourth is this, fifth is this, and so on, right? More these records are, more the experiences. The number of records is my experience, more data I have.
Right.
Features are like, what are the distinctive characteristics of each of those records? Make
Okay.
sense? More features does not mean more experience directly, right? More records or more data as such, data in terms of the number of records that I have, that means more experience. Now I can train a model with 100 records. I can train a model with 1000 records. I can train a model with 1 lakh records, right? So more experience is when I'm training a model with 1 lakh records. Make sense?
Yes, sir. Got
Yeah.
it.
So this is very, very important to understand. I will always have a set of input features and an. So how I'll get a data set? Data set only will have when I'm dealing with, okay, I'll talk about that in category when we will learn supervised learning. Then it will make much more sense, right? So as of now, you remember there's a data set. More the records in the data set, more the experiences, right? And we call all these, this car registration number, mileage, age, brand, has met with an accident or not, all these are termed as features. And maybe I might have a price here. Okay, this car is of 3 lakhs. This car is of 2.5 lakhs, 1 lakh, and so on. This is my label or output, right?
So based on these features, the price that we get is termed as the label, right?
Yes, that is the output basically. So what model will learn? If I feed this data, right, I will also feed these prices. What model will learn? Based on these values, there will be certain values for each record. So it will try to link a combination of these to the price. That's why I'm saying y, this is y basically. Label is my y, right? Y is f of this capital X. How do I break this capital X? X1, X2, X3, X4 up to Xn if I have n features. Right? So y will be a sum function of this, like maybe 3x1 plus 5x2 minus 2x3, something like this. It will come up, and that's my model. This equation will is my model. Make sense?
Yes, sir.
Yeah. See, instances or examples. We have already talked about. An example is a particular instance of data. One record is one example, right? We put X in the bold face to indicate that this is a vector. Vector in a sense, when I pick up a one record R1, it has multiple features, right? Car registration number, the age of the car, then maybe the brand, has it met with an accident or not, and so on. So this is all kind of a vector. We can represent it with a vector, right, mathematically, because there are multiple inputs to it. So now there are labeled examples, there are unlabeled examples. What is labeled example? A feature labeled example includes both features and the label. So you have a set of features, you have a label also. The way I was showing here, you have these records along with the price when it was sold. Maybe the first car was 3 lakh, 2 lakh, 1 lakh. So this label is already there with us. So these are known as labeled examples, right? Unlabeled is we don't have the price, we only have the set of features. We only have set of features, but we don't have the price. That is unlabeled. So y part is not there within the data set that is given to us. Understood? What is labeled example and unlabeled example?
Yes, sir.
Yeah. Fourth one, models. I've been using this term. What is model, right? One example I gave you, okay, model could be in a kind of an equation for predicting a house price, the examples, right, which I was just writing 5x plus 3x2 minus 2x3 and so on. So what's the model? Model is something which where we see machine learning is all about. It defines a relationship between set of input features and your output feature or the label. So I was saying y is equivalent to 5x1 plus 3x2 minus 2x3 minus 2x4 and so on, right? This is one model. Now, if I'm preparing a model for a spam detection, what it will do, it might associate certain features strongly with a spam. And let's look at the two phases of a model. One is the training phase. Training means when you have fed the historical data so that it learns certain patterns out of it. Right? That is, you show the model labeled examples and enable the model to gradually learn the relationships between features and label. Inference. Inference means applying the trained model to unlabeled examples. That is, you use the trained model to make useful predictions. So now model has trained, right? Now what happens is you feed certain unlabeled examples to it and it will make some predictions out of it. So you have historical data using which you have trained a model. Now you have got certain records for which you do not know the output. Maybe they're the new records, new incoming emails to my system, right? So that is unlabeled data coming to us, but I want to label it, right? That's what it is. Just give me a moment. Okay, let's continue. So training is historical data along with labels when we are feeding, right? That is model is getting trained. Inference is when we are predicting on unseen data. Make sense? Does it make sense? What is training phase? What is inferencing phase? Okay. Now, let us look at the types of learning, right? First, we talked about the level of supervision, correct? It could be supervised, it could be unsupervised, it could be semi-supervised, it could be reinforcement based, right? These were the phases which we talked about, right? Sorry, kind of different learnings that we talked about. Now, we have already gained some knowledge. Now, I will just categorize what is super learning based on that knowledge, right? I said we are given some data, and data has certain records, and those records also have labels, means the output part, like the house prices. When I give this kind of data which has a set of input features and its associate label or the output, right? Associate label and the output, that is my supervised learning. I have the outputs with me in the data set given to me, that is supervised learning. For instance, let's say spam detection. What do we mean by spam detection? We want to filter the emails, whether it's spam or not spam. So I have a set of emails with me, set of features of emails. So email features could be X1, X2, X3, and also I will have that Y feature with me, the output or the label, whether it was spam or not spam, right? When I have this kind of data, right, the labels are there. Okay, the first record, these are the features. Okay, this is spam, this is non-spam, this is spam, this is non-spam, right? Or let's say if I talk about house price prediction, I have Y label with me. Some a set of input features. Okay, this house price was sold in 2.5 lakhs. Okay, this was maybe 2.5 is too less probably for a house, right? Let me make it 25 lakhs. Okay, this house is 35 lakhs, or this is 50 lakhs, and so on. So what I have is label. What I have is label. When I train the model using this, right? So this is all supervised learning. Desired outputs or the labels are available in the data. When I have a data set, when I don't have these labels, right? When I don't have these labels, I only have set of input features. Now I want to do something with it. That is unsupervised learning, right? That is unsupervised learning. Typically, the applications of unsupervised learning is one technique that we cover is clustering. Let's say there is a retail store, right? Online retail store. It has lots of customers. Now, they don't know which are high valued customer, low valued customers, and so on, right? They don't have labels for it, high valued, low valued, and so on. Or high spend, low spend, medium spend customers, they don't have labels for it, right? There is some data available with them. So what they do basically is they try to find out the similarity between these set of customers and come up with certain groups. Okay, these set of customers fall in one group because they spend around maybe 10,000 per month. These set of customers, they fall in another group because they spend around 1,000 rupees per month, right? So in this way, it will try to group the data. It do not have the labels initially, but it will try to group kind of. That's unsupervised learning. I have data, training data only, but I don't have the desired output. I don't have the labels that these are high spend or low spend customers. No, that labels are not given to us. That is unsupervised learning. Semi-supervised is a mix of both supervised and unsupervised, where we have large amount of unlabeled data, which we use in unsupervised learning, and a small amount of labeled data also, right? So we have both kinds of data, but I don't have enough labeled data to make it supervised. I have lot of unlabeled data, but a small amount of labeled data also. So labeling data is a little expensive, right? When we have to do it with human intervention. So this approach is useful at many places where you have a lot of unlabeled data. You run an algorithm, you can verify it. I mean, you can use that labeled data later on to verify the things, right? Last one is reinforcement learning. Here, the model learns by interacting with the environment, right? Instead of labels, what it receives is rewards or penalties based on its actions. So the goal is to learn a sequence of actions that will maximize the reward. That's what it is. So this happens while you want to model problems such as playing chess. You want to win, right? Or any other video game. Then another example could be in robotics and autonomous driving, right? So you actually learn from the environment there, and you don't talk about labels and all those things, right? So these are the four different categories of learning, right? Now, within supervised learning, when I say supervised, we have labeled data with us. There are two kinds of problems that we solve. One is regression and other is classification. We have already covered the examples of this, so I'll keep it very simple. You want to predict the house price, right? The house price, uh, house price. Well, what is this output variable house price? Now, there are two categories of output variables. One is discrete, another is continuous. When I am predicting a continuous variable, like a price of a stock or a price of a house, my problem is a regression problem. When I am predicting a discrete variable, like spam filtering or recognizing handwritten digits, right? In that case, my variable is discrete. I have either spam or not spam thing. But in continuous, I can take set of infinite values, right? Here it is countable set of values, right? In discrete. So when I am predicting a discrete variable, that's a classification problem. But when I'm predicting an continuous variable, that is a regression problem. So anything related to predicting the house price or predicting the stock price, uh, predicting probabilities, right? That's again, the probability is also sort of continuous, right? So all these are regression problems. Classification, discrete variables, right? Now, can you give me an example of regression? Any other example of regression apart from what I have covered? Vasu, there is a question you have asked. Okay, you can please unmute and then speak also. I'll answer that. But can somebody first quickly give me an example of a regression problem and a classification problem? Whatever is there written here apart from that, or whatever we have discussed apart from that. Go ahead, please.
So regression can be the temperature,
Predicting a temperature. Okay, good.
then predicting our salary on the
Salary.
basis of experience and skills.
Is that a classification or a regression?
Classification, which is discrete.
Salary. Do you think salary is discrete? Salary is a real number, right? Real number can take infinite values. Maybe the salary could be 1 lakh, right? Maybe the salary could be uh, like if they do it like this way, normally they are rounding off, but these kind of figures are also possible, right? So salary is sort of continuous variable, not a discrete one. Now, if you want to predict whether the salary will go up or down, that becomes the classification, because I have two classes now, up and down. The down is not a possibility, right, when it comes to salary, but let's say stock market, stock price, even whether the stock price will go up or down, that's a classification. But when I actually want to predict the how much it will be, that becomes a regression problem. Does that make sense? See, other people can also answer, right? Only one or two students are answering questions. You can participate. Are you able to digest what I'm covering? This is very, very fundamental, right? Later on, I'll pick up the pace, but these fundamentals should be very, very clear.
For classification, maybe fraud detection.
Whether it is a fraudulent transaction or a non-fraudulent, yes, that's a classification. Good. Anybody else? What has happened to all of you? You are here to learn, right?
So category of products in a grocery store can be classification,
Yes,
and
categories are limited. Correct.
data, I mean data of their inventory can be regression, right?
Data in the
Like
sense,
sales data or anything.
sales data, you're saying you want to predict the sales, right?
Yes.
Good. You want to predict the sales value, right? That's okay. That's a regression problem. Yeah. Fine. So this is bit about it. Now, what is reinforced sequence or the output? What is reinforced is the feedback. You have taken an action. What is the feedback for that? Right? That is known as reinforcement learning. So there was a very beautiful story about it, right? There was a mice, right? And there was some food kept there. In between, right? Uh, Maybe when the mice reaches a particular stage, the mice can be given a shock, a bit of shock, right? And this was tried. When mice was searching for a food, okay, it has seen, okay, there is a reward. Food is a reward, right? And if it is going there, and you keep a food without giving a shock, it will go there, it will be happy, and the mice will be happy, right? Later on, what they tried a different experiment is they started giving a shock as soon as the mice will reach there. Okay, the first time it was given, so mice came back, but there's something wrong. Second time, third time, and all. And when they've started keeping food after, okay, 5, 6, 7 times, the reward given was a shock, right? Instead of the food, the mice learns, okay, the food is there, I don't have to go there. It stops going, even if the food was kept there. So it's a kind of reinforcement learning that has happened. You give a positive reward, people will go and, okay, take it happily, right? The moment you say, okay, this is kept here, and in between you are giving something, a shock, even the mice learns, okay, that I don't have to go there. After a certain number of iterations, it will say, okay, learn that I don't have to go there. Does that make sense, Vasu? What is reinforced? Okay, now let's look at regression. Let me see if I have something else. Okay, nothing like that. Okay, fine. What is regression now? Now, this is a 2D plane, right? Now, in mathematics, in your school mathematics, this kind of equation you might have seen. Have you seen in your school days? y is equal to mx plus c. Yes. What comes to your mind when you see y is equal to mx plus c? What this equation represents? Forget about this, what is there in the graph. Just focus on what I've written as of now. What this equation represents?
Equation of a straight line.
Exactly, equation of a straight line. So you have a 2D plane like this, right? So you can draw a line like this, right? And where m is nothing but the slope and c is the intercept, right, from where the line starts, right? This is the equation of a straight line. Now, this kind of equation you will get for a linear regression model when you have one input feature. When you have one input feature. Let's say I just want to predict the price of a house based on the area. So x1 is one feature, which is the area of house. Basis this, I want to predict the price. So what I'll write, y is equal to, right, some function of x plus maybe a constant. So this is how we represent it when I have one input feature. So m is the weight for that, how much that feature influences. Does it really contributing towards the output or not? Basis that, the value of m will vary. If the area is large, right, say, generally the price of the house will be more, right? So they'll have kind of a direct correlation. In general, I'm talking about. Rest the data will speak, because our model is going to learn from the data only, right? It's a very simple hypothetical example based on the area that we are going to predict, right? It will be a straight line as such. So what typically these supervised learning regression problems are, that you have to learn a model which will fit most of the points as such, right? Now, in this case, what is this? This is all our 2D points. This point will have an x coordinate, have a y coordinate. This point will also have an x coordinate and a y coordinate, right? Now, if you see here, these are the points. I want to fit a line that can pass through most of the points. Let me take an example here for a straight line. Let's say I have these points. I have these points, right? I can fit a line like this. And let me change the color also. I can fit a line like this. I can come up with a line like this. So there are many lines which I can pass through, but not every line will exactly touch each and every point, right? Not any straight line will touch exactly each and every point, right? But what will happen is, whenever I'm drawing a line, right, there are certain points. Now I'm drawing it with circle. Certain points will lie above, certain points will lie low, right, like this. And maybe few points may lie on the line also. So what will happen is, I'm going to draw a perpendicular from each of the points to this line, and this is what is the residual error with respect to that particular line. This is again a residual error with respect to this point, residual error with respect to this point. So I'll find out all these errors, right? Because I can come up with multiple lines. There could be infinite lines which I can draw to pass through a certain set of points, right? Not exactly pass through, but fit through certain set of points, right? But which line should I choose as my model? So what I want to minimize is, I want to minimize this overall residual error with respect to each and every point. So what I will do is, I'll find out the residual error with respect to each and every point and sum it across all the points. Whichever line will give me the minimum residual error, that is the line I'm going to pick, and I'll say this is what fits my model. When it comes to simple linear regression, where you have one input feature and one output feature. Does it make sense? In case I am going to predict house price based on one feature, that is, this is my house price in this direction, right? This is the area of the house in this direction. So I can come up with infinite lines when I am trying to predict, right? What is the relation between house price and the area? House price is a function of area. That's what we are saying. When there are infinite lines that can pass through, now which line should I pick? Which will give me the minimum residual error? That is the line which I want to pick. How to do that, that we will see later. But at this moment, that's what I'm simply trying to explain you. That is the line I'm going to pick, and I'm going to call it as linear regression, right? When you look at these set of points, so there is one straight line, that red one, which is passed, and there is one curve that is given, right? And if you see clearly, which one fits more to the set of points that are given? Is it the straight line or the curve which is fitting more to the set of points that are drawn? Is the line more closer to all the points or the curve? Which one fits better? I'm talking about this figure now. Please speak out. Otherwise, I'll not be able to understand whether you are able to follow or not. I'm talking about this figure now. These blue ones are the points, right? Red is the straight line and the green one is the curve. Is the green curve fitting these points better or the red line? Curved green line, right? The curved ones. That is fitting better, right? That's good. That's what I was expecting, right? So curve is fitting better, which means that it is a regression model, right? It is a regression problem, but it's not a linear regression because I'm getting a curve. The function of the curve could not be linear. It will be something different. You must have studied in mathematics, right? Curved functions. This could be something different. Maybe I have to go to a square, quadratic function, right? And then it will fit, right? So what I mean to say is, using regression, I have to figure it out whether a straight line fits or whether a curve fits, right? I have to start my models with x raised to power 1, then x square, then x cube, and then I'll try to keep on fitting this and see where I am getting the minimum residual error. That's what I'm looking at, right? Does that make sense? Curve will give me lesser error because it is fitting to the points. It is taking to the shape of the points as such. The diagram which I have drawn, right, that was more of a straight line fit. Does that make sense? Somewhere the curve will fit, somewhere the straight line will fit, somewhere even more complex things will fit. That we will see as we progress. But that's a regression thing, right? Look at this classification thing. When I try to draw the points, right? Let's say the classification data I draw at certain points and I got these, right? Now, what I've got is let's say there is a tumor, whether the tumor is benign or malignant, right? Based on the tumor size, I'm going to classify it as whether it's a cancerous or it's a normal thing, right? So the red points are, it's a benign, right? Sorry, yeah, malignant, right? While the blue ones is, you can say, the benign part, right? So when y is equal to 0, we are saying benign. When y is equal to 1, it is malignant. Now, I have plotted this. I want to draw a boundary which will segregate these two. That is my classification. Here, I wanted to fit a line which will pass through most of the points and give me the residual error. But here, I wanted to draw a boundary basis which I can say, okay, points lying above this boundary are benign or malignant, or below this, so and so, right? So maybe if I draw a line like this, straight line like this, right? This boundary. And this boundary will indicate any point lying above this is a cancerous tumor, while below this is non-cancerous. So I have to come up with that decision boundary. And then whenever a new point will come, I'll just plot it. I'll see on which part of the decision boundary it lies and do a classification. So you see, if x is greater than t, malignant, else benign, right? So some model will, what model has learned is, if the size is greater than certain value t, then malignant, else benign, right? That's what it is. Look at this. It could be multi-dimensional also. It was 1D kind of a thing where you have horizontal points kind. It is a 2D kind of a thing, right? You have points here. But this is my decision boundary then. This straight line is decision boundary. If the point lie on the right side of this decision boundary, it is categorized as malignant. Below this is a benign, right? So in case of regression, I'm trying to fit a line or a curve or a function, right? Here I'm trying to come up with a decision boundary, and that decision boundary will also be sort of an equation, right? Which will represent, okay, if the points lie in this area, I can categorize them as this. If points lie in this area, I can categorize them as this. That's what it is. That's the basic difference. Does that make sense? What we are doing in classification and what we are doing in regression? At this moment, if you have any fundamental question, you see, okay, I'm not able to grasp this, please speak out right now. If you are able to follow, please let me know. In that case also that you have followed. Hello. See, keeping quiet is not an option. You have to speak out or write it in the chat box. Vasu, Shweta, Shreya Sarkar. Okay, got it. Fine. These are the techniques which are classified as supervised learning techniques, right? As of now, you just remember these names. What are these? Some of these techniques definitely we will cover in this course. So first one, I have already named it linear regression. When it is a straight line fit, right? That's a linear regression. Then comes is logistic regression. Logistic regression is not coming up with a line and all, right? It's not about predicting a continuous variable. It's a, though it is named as regression, but it comes up with a boundary, right? Below which the points are classified as this, above which the points are classified as this, right? So that is the case with logistic regression. It's a classification technique. Then comes is naive Bayes classifier. As the name indicates, right? Classifier. So it is also going to come up with a decision boundary for a classification problem, right? Then is support vector machines. This is again a classification problem. Right? Then we have decision trees and random forests classification problems. Neural networks, we can actually model very complex and nonlinear patterns using neural networks, right? And especially useful in deep learning applications. So different algorithms, these are all the algorithms or techniques, are used for the different type of problems as well as data. Now, choosing the right technique is an important step in building an effective machine learning model. Maybe you might have to try 2-3 models and then come up with it to a conclusion, right? But we will see some of these techniques definitely in this course in detail with mathematics. Unsupervised learning. As I mentioned, you don't have labels here, right? But what you can do when you have unsupervised learning is you are only given a set of input features from x1 to xn without any labeled output y. You don't have that. Now, how do you train your model? So what you can do is, the goal is not here the same as what we have seen in supervised learning approaches. So instead of predicting an output, what the model tried to do is to discover some structure or patterns in the data. And one good example is clustering. As I said, it will try to group. Now, when you visualize this, right, these are the points. You know, these are the points very close to each other. I can group them into one. These are the points close to each other. I can group them into one. These are the points close to each other. I can group them into one. And this is what the kind of clustering it will do. 3 set of groups it will come. And this is very, very useful when I want to do target marketing, right? Target marketing means I have, because marketing comes up with a cost, right? You want to reach out to certain segment of customers who are likely to buy your new product. But whenever you set up a marketing campaign, it will come up with a cost. And looking at the price points and all, you want to target the certain specific customers. So you will group them into 3. Out of that, you can pick 1 or the 2 groups to whom you want to target as such and how you want to target, right? So what model does is it tries to find out the natural groupings within the data. So these are the unsupervised techniques. One is clustering, which we have talked about, and these are the algorithms for that. Hierarchical cluster analysis, k-means, right, expectation maximization, these are all algorithms. Then within unsupervised learning, we also have another set of algorithm, that is dimensionality reduction, right? So what happens is when you have a lot of dimensions, when I say dimensions, right, it means lot of features I have in the data. That n value, right, x1, x2 up to xn, these are very, very large. Maybe I have 1,000 features in my data, right? So imagine you have 1,000 columns in the data. This is too much, right? And if you want to visualize it, visualization becomes very, very difficult. So what you try to do basically is you try to represent the, out of those 1,000 variables, you pick certain and try to represent with some representation that is easy to store and represent, but at the same time does not lose too much of information. I am reducing those features, but at the same time, let's say out of those x1, x2, x3, x5, right, or x20, let's say for 20 features, I am coming up with some equation which represent these 20 in one go. So out of those 20, I'm creating one feature out of it, which has the information of all 20, right? So I'm trying to reduce. I'm trying to reduce. One example I'll give you. Let's say I have height of a person. I have a weight of a person, right? Can I represent these two with a common feature? Do you know that common feature using which I can represent this? There's one term used for this. I know the height of the person. I know the weight of the person. But can it be represented with some common feature? What is height divided by weight? What is height divided by weight? Have you heard this term?
So body mass index.
Yeah, right. Correct. So I'm able to represent that information, right? Instead of using two variables, I'll use that PMI part, right? So there are techniques like principal component analysis and all, locally linear embedding and T-distributed stochastic neighbor embedding and all. These are some names, right? You can remember these names as of now. Some of these things we will cover as we progress in this particular course, right? We want to reduce that feature space, right, as such, and it will reduce the computations of the model, as well as you are not going to lose too much of the information as such. That is what it means, right? Then the third category is for unsupervised learning is association rule mining, where I said, okay, you can find out certain rules. I think last time I gave you an example of beer diaper, right? A determines B is one rule. So it means that if certain person is buying an item A, he's likely to buy an item B. This is association rule, right? Somebody has bought a bread, he's likely to buy a butter. I'm going to find out certain rules out of the data set, right? I don't have the labels, but I am coming up with these rules from the data set, and that's what is association rule mining. And these are the two techniques that we use, ACLAT and a priori, right? Then comes is the visualization, right? Data visualization. So typically what happens is in many scenarios, when you have very high dimensional data, right, it is very, very tough to interpret it directly. And that's where the visualization becomes important. You try to visualize the data, and we try to represent the complex high dimensional data in 2D or 3D so that as humans we can understand it. But what are the key objectives that we have to see while visualizing this, right? We want to preserve the structure. I am reducing the dimensions, maybe using principal component analysis or some other techniques which were listed in the last chart, but we try to retain the original relationships between the data points. So we want to preserve the structures as much as possible. Then understand how data is organized, right? That's also very, very important. So you have to see how they are naturally grouped. Maybe, for example, like animal like cats, dogs, and deer. This is animal group may go into one, right? If I have set of vehicles also, maybe car, truck, airplanes, they will go into the one group, right? So that's natural groupings or differentiation that we should be able to see, right? And that's what it is showing here also. Then last point, very, very important, is identifying hidden patterns. That is something, some patterns which are not obvious in the raw data, but it becomes visible when you do visualization, right? Another thing that we can do is when you look at this particular diagram, right? If you look at these set of data points, these set of data points sort of are kind of close to each other, right? And we can say these are all normal. Some points lying here. It's very far away from these points. We may categorize them as normals, and this can be an anomaly or an outlier. For example, let's say most of the students in a class have a CGPA ranging between 6.5 to 7, and suddenly we have a student who has 9.8 CGPA, right? That's a kind of an outlier for class. So those things becomes visible from these visualizations, right? Directly. We have already talked about this association rule mining, right? So you are given a set of transactions and you want to come up with certain rules. Here it is mentioned that item 2 employs item 3, meaning that if somebody has bought item 2, he's likely to buy an item 3. How we have derived this rules? From the set of transactions. So you see in how many transactions item 2 and item 3 are bought together, right? That's what it is. So many transactions we find out where item 2 and item 3 are bought together. It's also known as market basket analysis, right? This is very common data set that we use, right? We might come up with this kind of a rule. Diapers implies beers. Somebody who's going to buy a diaper, he's likely to buy a beer also, right? So you see in this data set, these are bought together. Though there is no common sense, okay, between diaper and beer, we should run a promotional offer and so on, right? When it comes to maybe a toothbrush or a paste, we can run a promotional offer, cross-selling. We can pack them together, okay? We can give them a free brush along with toothpaste in order to increase the sales of a toothpaste as such, right? But beer diaper, it's not very common sense kind of an association, right, as such. But this is what data speaks. We have to go by the data, right? This is very important. I mean, you can even Google it out. This is another example of this unsupervised learning is where you want to group the individuals by genetic similarity. So you want to check their genes and then which are highly similar, you want to group them. So you can see these all green ones, red ones, and different color ones as such, right? These are another 4 examples that I want to organize computing clusters. I want to do social network analysis, right? I want to do market segmentation, astronomical data analysis, where I don't have the labels basically with me. That is when I will make use of unsupervised learning. Next is semi-supervised learning, where we have partially labeled data and a lot of unlabeled data. So it will combine supervised learning algorithm as well as unsupervised learning algorithms. Both it will combine them together and form another one, semi-supervised. So the core idea is instead of relying on the labeled data, we use a structure of unlabeled data to improve the learning, right? There's a lot of unlabeled data I said, right, which is easily available as such. So what do you see from here is, if you look at this, there are certain gray dots, there are yellow ones, there are green ones and all. So gray dots is largely my unlabeled data. I don't have the label for that. Green ones, the triangular ones, they are given some label. The square ones and the yellow ones, they have also labeled data, right? Color images, triangles, squares, they have a image data, right? Now this new data point X. The question is, what class should this new point belong to? How do I figure out that, right? Now, how the model will look at? The model will look at the nearby labeled points, the overall structure of the clusters formed by the unlabeled. You see, right, this is a sort of one boundary that I can make here, these particular set of points. And these particular set of points, I can make another boundary, right? Those, I don't know the labels of these gray points, whether they are triangle or a square, right? But using this, you can see these can be grouped into one, these can be grouped into one, right? So I can define the cluster boundaries. And now what can happen is, I know these points are more close to this triangular ones, right? So I can categorize this as a triangular ones and this one as the square ones. So I'm able to sort of categorize both. typically, let's say you have some application, you have some photos, right? We click photos as such, right? And nowadays there's an application. Uh, it is able, from the faces, it is able to detect how many such photos exist for that person. And if you click on that face, it will retrieve all the photos, right? So based on the similarity, it is able to find out. Now you want to label it a certain person, right? Because our human eyes can label it. We can label it, right? That's a person A, right? That's a person B, right? So this is what we can do. So from an unlabeled data, we are able to find a group also. But at the same time, we want to label it because we have the labels available. So sort of an automatical grouping that is happening. So unlabeled data is helping me to reveal the structure. As such, these set of points are similar to each other, while the labeled data provides the guidance. This is this particular category and this is this particular category. So semi-supervised kind of learning is useful when you have lot of unlabeled data and small amount of labeled data. That's what it is, right? I hope it is making sense. Is it making sense? Semi-supervised, unsupervised, supervised. Three we have covered. Okay. Now, when you look at semi-supervised learning algorithm, we've seen it's a combination of supervised and unsupervised that we've already seen. So the model learns the structure from the unlabeled data and then it uses the labeled data to refine its predictions. That's what it does, right? So another good example is deep belief networks, which are based on unsupervised components, are called restricted Boltzmann machines stacked on top of one another. Right? So this is a kind of a network, right? That can be an example of semi-super, but we don't know what is deep belief network as of now, right? So probably it will be difficult to understand. So what is these machines are? These are trained sequentially in an unsupervised manner, right? They don't know the correct labels. You simply feed the data, it will try to group them, kind of a thing, right? Then once they have learned that unsupervised manner, right, then whole system is fine-tuned using supervised learning techniques. So we will use the label data to improve the accuracy. And now here we are able to categorize it, right, correctly. But what if there is a certain point in one group which is saying that, okay, maybe there is a certain point here. Right? From the natural groupings, when I see, okay, these are the clusters and these are the clusters here. When some point is here, when I have not used the label once, right? And it is, let us say, the triangle. From the natural groupings, it will form these two groups, but where this will go, right? This is a triangle, then I need to change the boundary of it. I have to go a little bit like this and include it, right? That's a refinement that I can do. Right? So we will talk about those things later, little more in detail. Reinforcement learning, as I gave you an example, that the system learns from the environment as such and changes its actions based on the feedback that is given. You remember that mice example, right? So it's a kind of an agent, a learning agent, right? Agent learns what to do by receiving rewards or penalties for its actions. If mice was allowed to take the food, it will go, right, for every time. But when the shock was given, after certain a number of times, it stops, right? So it observes the state of the environment, select and perform actions. So there is an agent involved here, which is the learner, the mice, right? The environment, the word that agent interacts with, and the state, the current situation of the agent. Action is what it chooses to, right? And the reward is in the form of a feedback, which could be positive or negative. So over a period of time, it learns the best strategy to get the most reward over a period of time. Right? So these are the examples: game playing, robot in a maze, balancing a pole on your hand. All these are good examples, right? So this is observe, select the best action policy, right? Environment, heat is there as such. This is an agent. If the tap is open, whether I should go, right? And kind of uh, look at this. What is happening here is basically this is an agent. Agent moves towards this fire, right? As such a decision taken, but the reward given is minus 15 points. So, right. So next time what will happen is it will avoid. It's kind of the same my story, right? Update policy, learning step. Iterate until an optimal policy is found. That's what it is. The robot moves in the environment. If it is going to touch fire, negative reward, right? So robot will learn avoid fire next time and maximize the total reward, right? Reward is when the reward is reduced, so it is minimizing it, right? But the goal is to maximize it. But next time it will learn that as such, right? It will not touch the fire. Now, based on how the training data is used, we have batch learning, which uses all the available data during the training. Mini batch learning uses a subset of available data, right? And incremental learning is there also. Three kinds. These things will come time and again, right? Don't worry about it as such. So these things will keep on coming. So you look at it, right? When I said, now you see mix of triangles and all, right? So you see the decision, how the decision boundary is being molded, right? So look at this. So there's an instance-based learning, compare new data points with the known data points and then do it. This is instance-based kind of a thing. This is a model-based kind of a thing, right? The model has a decision boundary. Anything falls in this is a triangle, anything falls in this boundary is a square. Instance-based is, there's a new instance, but what will happen is it will compare it with the nearby object and try to classify, but it may go wrong also, right? That's what they are trying to infer from this. I think it's 11:05. We should kind of wind up. How much time is like? Okay, a lot of things are still pending. Anyway, I'll spend time on these things. Maybe we can have extra session someday later on. But these are some of the things which we should learn. Still, we are at session 1 only, right? But revise these concepts, please. Right? I'll spend some time on these more. So once you have the basic fundamentals ready, then we will pick up the pace, because all it's about training later on, training and validation, right? A lot of mathematics will be there. Okay. Did you learn something from today's session? People are very fast to quit, right? I think it is 11:15 the next session. I just want to understand few things. Did you get something out of today's session? Yes or no? Vasu, have you taken down notes? Not today. Please keep taking notes. Divija, Shweta, Sai Dhanush, looking forward to some feedback. Are you able to follow some basic fundamentals? Because when I asked in the first session, all of you said that, okay, we are not very much familiar with this field. So I'm going slow at this moment. From next time, I'll pick up the pace. I'll not repeat many things, right? So we will start from here. Challenges of ML as such, right? These are the three parts left. Very, very important from practical standpoint. So I will spend some 15-20 minutes on these 3 points first. Okay. Then we will work towards framing an ML problem. That's all I would say. All right. All the best. Let's meet up next weekend, right?